Hello, everyone. So in this video, we're gonna explore a problem from MathCON, but to do so, we are gonna prove some relation and then see if we can kind of get the problem immediately after. Okay. So to start with, I'm gonna draw a triangle in a circle, which we have a name for it. We call circumscribed triangle. So if you were like have a triangle inside of a circle, right? So let's say this is the circle, and I'm gonna start with a acute angle triangle. So let's say this is my triangle. If I have this triangle as acute angle, right? And my goal is just to find a relation between the sides and the radius of the circle. So let's say this is the center of the circle, and our goal is just to extend the law of sine to get another relation, and then using the law of sine and the sine and area approach to find another relation to get the radius of this circumscribed circle. Okay, so let's see what we have. So first things, I'm gonna label this is A, B, and C. And I'll say this is side C, and then that is side B, and then this is side A. And if you remember, like law of sine like states, the sine measure of a angle divided by the opposite segment is equal for all three. But I'm gonna do the other way around, which is I'm gonna divide side A divided by sine A. Okay, this ratio is equal to B over sine B, and that is equal to C over sine C. And our goal is just to extend this relation to the radius of the circle that is outside of the triangle, which we call circumscribed circle. And our goal is to make this equal to something else in terms of the radius of the circle, okay? So the first thing we have, I start with this triangle to be acute angle. So I do like to make a right triangle because I do know the sine value of 90 degrees. So to do so, let's go ahead and draw the diagonal because that will help us a bit. So if I extend this, let's say diagonal, okay, let's assume this is my diameter, not diagonal. Okay, I'm gonna name this as D. And if I have a like angle that is facing towards the diameter, we know that that is going to be 90 degrees, right? So what I mean by that, so if I connect the point D to the A, for example, the angle in between DA and AC, which is DAC, is going to be 90 degrees. So if you don't really know about this, this is just the definition of the inscribed angle, because the angle DAC is facing towards DBC arc. So that's just the 180 degrees. So that will be half of that, which is 90 degrees. So why do I need that? Because I'm gonna use the law of sine, and then I just need something in terms of the angle measure. So 90 degrees does help. Okay. So now if I name this radius is R, okay, so if the radius of this circle is R, O to C, then DC is going to be 2R, right? So let's go ahead and use that. If I want to use a law of sine in the, like this triangle, I got this relation, right? So what I like to do now, you know, the angle measure right here, angle D, which is a inscribed angle, this has to be half of the arc measure of AC. So the angle measure of ADC is equal to 1/2 of the arc measure of AC. Okay, so that's just the definition of the inscribed angle. But at the same time, AC is also like between the chord BA and BC, which is why the angle at B is also equal to this angle D. Okay, so that is also equal to the angle D. So I'm going to say this is ABC. And if I just want to use the like law sign in this triangle, the right triangle, so here's what's going to happen. So the side DC, which is the diameter, is 2R divided by the opposite angle is 90 degrees. So divided by sine 90 is equal to, if I want to use this angle and then the opposite side is B, so that should be B over sine D. Since we know sine 90 is just 1, so we can replace that. And then if I want to find the like sine D alone in this equation or B alone in this equation, so I will get what I want. So like if I want to take the sine D alone, which is same as sine B, which we are going to replace right there. Okay, so let's plug, like let's swap these. So then this equation will give us sine D is equal to, if I take this 2R to denominator and sine D to the left side, so you just get the B over 2R. Okay, so this is something. So if I like remember the angle B and angle D were was equal to each other because they are just facing towards the same arc. So the sine D is actually the same as sine B in my figure. And if this is the case, I can replace sine B with B over 2R. So B over sine B can be written as B over like this ratio. So right, but if I plug it right there, so B over that, sine B equals that. So let's do that. So what B over sine B, B over sine B is this, so B over 2R. And this is equal to like B over sine B is just B over 2R. So I just write this guy basically right here. And that will give us B over 1 times 2R over B. So the B's will cancel. You got, that's 2R. So meaning that this ratio is equal to 2 times R. So I hope that wasn't too complicated. So just look at this one more time if you didn't get it. And that means the ratio of B over sine B is equal to 2R, since the other 2 is also equal to this ratio. So that means all 3 is equal to 2R, which is something nicer because we do have now a relation. The law of sine now extended to the radius of the circle that is outside of the triangle. And if I have this acute angle triangle, I can make a deduction like this, like I can make a right triangle, and I can see that one of the angles will be same as this one. I can use this idea to prove that is the case. But if this was a right triangle, that is already obvious, so that's going to be less work. But if this is not acute or right triangle, we should have a obtuse angle triangle. We can still have the same reasoning. I'm going to leave that for you as a challenge to discover if you can prove that piece as well. But this is going to work with obtuse angle triangle as well. Only thing that you're going to need, just the sine measure of like one angle is equal to sine of the complementary of that angle, which is 180 minus alpha if this is in degrees. And by using this, we are going to actually able to show this is also true for the obtuse angle triangle as well. But now let's try to drive another relation of the area of the triangle. So if I have a like triangle, any triangle works. So I'm going to name, let's say this is the altitude. Okay, so I'm going to name this is A, B, and C. So if this is height, and I'll name this is H. So this is B, C, and A. And if I want to find the area of this triangle ABC, which is, I'm going to use the like a square bracket to say to present the area. And I like to multiply the height by the base and divide it by 2, right? So this is what we usually do. It's going to be A times H over 2. But the question is, I like to kind of not use the h in my formula. I like to use the sides and angles. So if I take this angle, and then if I use the sine c, so that will give us like this. Sine like c is equal to opposite side over hypotenuse, which is h over b. If you multiply both sides by b, so the h would be b times sine c. So now we have the h as b times sine c, so I can replace h with that. So this is going to be equal to 1/2 times a, and h is just b times sine c. And now we have another like way to find the area of the triangle if you know the two sides and the angle in between those two sides. So the reason why I kind of show this one as well, because we're going to combine this one and the extended law of sine to find another, I would say, relation. So we already know like c over sine c equals 2r, b over sine b is 2r for any triangle, and then we can use this area approach in any triangle. So for that reason, let's try to combine those. ABC, the area of a triangle, is equal to 1/2. My goal is now to find the area of the triangle just using the ABC, which is the side, plus the radius of the circumscribed circle, okay? Just to see if there is a relation between those. And I do know the area was the A times B, right? Times B. And then instead of sine C, I'm going to find the sine C in this equation, get it along. Okay, so think about this part. If I want to find the sine C, like I can take this 2r and divide by 1, so I can swap these and then put sine C alone, and then that will give us the sine C is equal to c over 2r. So now I'm going to replace this into this equation. So instead of sine C, I'm going to replace c over 2r. So that will give us c over 2r. And now our new formula is 1/2 times 1/2 is just 1/4. And then ABC. And then there is a r, so I can write it as 1/4r. So better way to write this maybe a times b times c divided by 4 times r. So again, this is a formula in some places you might see already. This is like the r is the radius of the circle that is outside of the triangle. So in this ABC. So and then if you know the three sides of a triangle, and if you draw a circle around it, the radius of the circle, okay, and then the sides of that triangle is somehow related to find the area of the triangle as well. So which is just another way to find the area. I did all of this just to kind of remind something, but when you really understand this, I really recommend you to try these on your own and see if you can get all of these relation. And here's the actual problem that we are trying to do. And the question asking, find the radius of the circumscribed circle of the triangle that is given right here, right? So based on the previous like deduction, I would say we have 1/2, like not 1/2, 1/4, like 1/4 of the product of the sides, so a times b times c divided by 4 times r was the area of the triangle, right? So this is the area of the triangle when you have the circumscribed circle. So we don't see the circle, but you can draw a circle around it. So we are looking for the radius of that. So if I know the area of this triangle, and then I can use the size to get the radius, which is what we are going to try. So like the area of this triangle, there are a couple of ways, but one of the ways is we can just use the height and base. Like if you just go ahead and count this, this is going to be my altitude, 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 times 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. That's 12. So that should be 12 units, and divided by 2, and that's 48. So we know the area is 48, right? And what I need is ABC as well. So since we know this is 4, and this is 8, and now we already know this is also 8. So we can use the Pythagorean. And if you have the 1 to 2 relation, I'm not sure if you know, but the hypotenuse will be smaller like times root 5, which is 4 root 5. It's good to know. And if you don't know, you can just use the Pythagorean anyway. And then this is 45, 45, 90. So that should be 8 times root 2. And now we have all three sides. So based on that, we can just apply the A. Let's say this is 12. And then B is the side, this one, which is 8 root 2. And then C is 4 root 5. And this whole thing is divided by 4 times radius of the circumscribed circle. And this is equal to 48. And I can write S over 1. So, you know, we have 4 and 12, which is 48. So this can be canceled with this, because when you cross multiply, those are going to be on the other side. We can just immediately cancel now. And this will cancel. So you got 2 and 1. So 2 times root 2 times root 5, which is 2 root 10, over r equals 1. So that means this is our r. So that's choice C. So again, the question was a like challenging problem, especially if you didn't know about this I guess relation. Then this could be a really challenging problem. I hope that is clear at this point. But as I mentioned, please try to kind of show the previous relation if you have never seen before, and see if you can get those, because if you try those, you're not going to lose them easily. So that would be helpful. Okay, I'll see you in the next video.